Assalamu alaikum students. Today we start topic groups. The first definition in this topic is groupoid. Groupoid is a non-empty set on which a binary operation is defined. It means if a clear property hold in a non-empty set, then is called groupoid. We have example 1. We have there even and odd numbers. In last exercise we have solved this. If we apply on this set binary operation with addition binary operation, then it's satisfied. Therefore this set is groupoid. Clear property hold on this set. Therefore it is groupoid. Next example is a natural number with respect to subtraction. We have two numbers 4 and 5. 4 minus 5 is equal to -1, not belongs to n. Therefore n means natural number minus binary operation is not groupoid under subtraction. Next we have a set 1 minus 1 iota minus iota is called fourth root of unity closed with respect to multiplication. It means if we apply clear property with respect to multiplication, it's satisfied and therefore it is groupoid. If we multiply any of two its element, the answer also belongs to the set. Next is semigroup. If a set is non-empty and satisfy two properties, closed means clear property hold with respect to multiplication, or we also say groupoid, and second one is associative. If a set satisfy two properties, groupoid and associative, then it is called semigroup. Now here we have example n natural numbers and binary operation is addition. If we apply associative property on it, it's satisfied. Therefore it is a semigroup because it is also a groupoid and associative property also hold. Therefore it is semigroup. Next is integers and binary operation is there multiplication. If we have any two integers, we multiply them and the resulting answer also an integer. And associative property a dot b dot c, a dot b dot c, a b c, any three integers, this condition also satisfied. Therefore integer with respect to multiplication are semigroup. Next example is PS mean power set of S. If S any set contain any elements, any number of elements, then its power set. Just like we have S contain two element A and B, then its power set is empty set A, set B and AB. And if we apply on there with respect to union and intersection, the set is semigroup and also semigroup on intersection. We will done this example in exercise also. And next third definition is monoid. First one is groupoid, then semigroup, and now it is monoid. If a set is closed with respect to multiplication, if a set is closed with respect to multiplication and multiplication is also associative, binary operation, and it contains identity. If three conditions hold in a set, then it is called monoid. First one is clear property, second is associative, and third is identity. If a set contains these three properties, then it is called monoid. Now again, power set PS, a set S is monoid because in last page it is semigroup, and if it contains identity with respect to union, then it is called monoid. Here example, in power set we have a set phi, and phi union with any of the set of PS, it becomes the same, therefore phi is identity and this set is monoid. Next is set of all negative integers. Contain 0 because 0 always on positive side. Now it is clear that with respect to addition, clear property hold. If we add any two negative numbers, the answer also a negative. Therefore, it is clear property hold are closed with respect to addition. Next is associative. Associative also hold if we apply associative on these sets, these numbers, and 0 is the identity of the set because 0 add in any of the number, it remains same. Therefore, this set is monoid. Now, definition of group. Now we have four properties. First one is groupoid or closed. Next is associative or semigroup. Third is identity or monoid. And fourth one is inverse. If a set satisfies these four properties, then it is called group. And if a set satisfies another property, commutative property, fifth one, then it is called abelian group. If a set satisfies first property only, is called groupoid. If it satisfies first two properties, is called semigroup. If it satisfies first three properties, is called monoid. If it satisfies the first four properties, is called group. And if it satisfies all properties, is called abelian group. Now here we have an example of natural number with respect to addition. Clear property hold, associative property also hold, but third property identity is 0, not in natural number, and fourth property is inverse of 2 is -2, not in natural number. Therefore, natural number with respect to addition only satisfy first two properties. therefore it is semigroup. Next example is natural number with multiplication. Clear property hold, associative also hold, and third one is identity. One is identity also in natural number, but fourth one is inverse. Inverse of multiplicative inverse of 2 is 1 over 2, and 1 over 2 not in natural number. Therefore first three properties only hold, and it is monoid. Now here we have a set 0, 1, 2, and operation on it is addition. And it is a module of class 3. If we draw a table, and here we have a table 0, 1, 2 and 0, 1, 2 on vertical and horizontal side. If we add 0 in all these number, the number are same, and if 1 we add 1 plus 2 is 3 because it is residue of 3, and we minus 3 from 3 it become 0, and last number is 2 plus 2 is 4, but if we subtract 4 from 3 it become 1. All entries of the table belong to the set, therefore it is closed with respect to addition, therefore it is also a groupoid. Next is associative. Now we have three numbers, arrangement like associative, and solve these. Both sides are equal. Associative property also hold. The set is semigroup. Next is identity. For addition, always identity is 0. For inverse, then we find the pairs which shows the answer is 0, and from table we see 0 plus 0 is 0, 1 plus 2 is 0, and 2 plus 1 is 0. It shows inverse of 0 is 0, inverse of 1 is 2, inverse of 2 is 1. And next, commutative property. 1 plus 2 and 2 plus 1 remain same answer. Therefore, this set is an abelian group with respect to addition. Next we have the same numbers 1 minus 1 iota minus iota. These numbers are called 4/4 root of unity, and we draw a table for with respect to multiplication. And there is a point to note, if iota multiplied by iota it becomes iota square, and iota square is equal to -1. In first line we multiply 1 with all these numbers, then -1, then iota, it becomes iota minus iota, iota square is -1, and minus iota square is 1. Then we multiply by minus iota with above 4 numbers, and we get the answer. From table all the values belongs to the set, same values according to the set, therefore it is closed with respect to multiplication. Associative property, if we apply three numbers then we get the same answer, and associative property hold. Here multiplication, therefore 1 is identity, because if we multiply with 1 the answer is always same. Next inverse, then again we find the pairs which show the answer equal to 1. From table we see that 1 multiplied by 1 is answer 1, -1 multiplied by -1 is 1, and iota multiplied by minus iota is equal to 1, and minus iota multiplied by iota gives answer 1. Therefore, inverse of 1 is 1. Inverse of minus 1 is minus 1. Inverse of iota is minus iota. And inverse of minus iota is plus iota. And last one is commutative property. Commutative property also hold, therefore this set is an abelian group. With respect to multiplication. Now here we have example. We contain a set in G 2 cross 2 non-singular matrices. Non-singular are those if their determinant is not equal to 0. Now this set contains matrices of order 2 cross 2. Now if we multiply two matrices of order 2 cross 2, answer remain 2 cross 2. It means clear property hold. Now we have three matrices A, B, C. If we multiply in like that, A multiplied by B multiplied by C, in both sides three matrices are multiplied of order 2 cross 2. At the end their order is same, therefore associative property hold. And 1 0 0 1 is an identity matrices. As in the question we have non-singular matrices, therefore all the matrices contain their inverse, but commutative property not hold. In matrices, commutative property in general not hold, because if we multiply by AB multiply by BA, the answer always different. Some exceptions are hold. Therefore first four properties are satisfied, therefore it is a group, non-abelian group. Next, finite and infinite group. A group is finite group if it contains finite number, and infinite if it is infinite number of element. Cancellation law, AB is equal to AC. We eliminate A from both sides, either on left side or right hand side, but mathematically we have done like that. We multiply A inverse on both sides. And inverse of A multiplied by A. If we multiply any number with its inverse, it equal to identity, and identity multiplied by any number, the number, if we multiply identity with any number, the answer is same. Now some solution of linear equation. We have Ax is equal to B. We multiply both sides by A inverse, and A inverse into A is equal to identity. And therefore it shows the answer x is equal to A inverse B. And this is the law of inverse. We apply associative property And the same rule, a number multiplied by its inverse, it becomes identity, and if identity multiplied by any number, the number is same on answer. Here is a theorem. G is any set, store is binary operation, is grouped with E identity, then we show that E is unique. In all sets, identity is unique. Now here is we two identities, E and E double dash, and we try to solve these. If E dash multiplied by E, the answer is same is equal to E dash. Here identity is E, and if identity is E dash, the answer is E, but the both are same because both are identities, therefore the identity is unique. Some example for this: integer with respect to addition contain identity is 0. Real number minus 0 means a set of real number except 0. We eliminate from real is 0. With respect to multiplication, then its identity is 1. C plus means complex number. With respect to addition, their identity is 0 plus 0 iota. And C dot means complex number. With respect to multiplication, their identity is 1 plus 0 iota. M2 means matrices of order 2 cross 2. Their identity is 1 0 0 1. Now same like identity, inverse also unique. Suppose A dash and A2 dash are two inverses of A, then A dash multiplied by identity, and in place of identity we can write A multiplied by A double dash. Apply associative property. This is also equal to E, and at the end we get the answer A dash is equal to A double dash. Example, in a group Z plus, inverse of 1 is minus 1 and inverse of 2 is minus 2. Inverse also always unique. In real number except 0 with respect to multiplication, inverse of 3 is 1 over 3. Now we start exercise 2.8. Here we like examples, same question. We have a set 0 1 of module 2 and we draw its table. It's residue module 2 class, and if we add 1 plus 1 it shows 2. Because it residue module of 2, we subtract it from 2, it shows 0. All the entries of the table are belongs to the set, therefore it is groupoid. Next, associative property also hold in this set. Identity element there is 0 because addition. Inverse of 1, 0 is 0 and 1 is 1. Commutative property also hold, therefore it is an abelian group. Now here same example like question. Set of module 3. If we draw first table, then from table we write its properties. Because it is module 4 and we subtract the 4 and greater than 4 values from 4. From table clear property hold, and we also solve for associative property. Identity is 0 and which pair shows answer equal to identity. They are inverse of each other. Commutative property also hold, therefore this set is a abelian group. Now here we have some sets and we have to write they are group or not. We already done in example. Again we have even and odd numbers and we draw a table with respect to addition. If we add even plus even, it is also even. Even and odd is equal to odd, and if we add odd or even, it is equal to odd, and odd plus odd is equal to even number. From table clear property hold, associative also hold there, and identity is there even number, because even plus even is equal to even and even plus odd is equal to odd. Inverse of even is even and odd inverse of odd is odd. Commutative property also hold, therefore this set is an abelian group. In example we done fourth root of unity, and now these are cube root of unity, 1 omega and omega square. So first of all we draw its table, 1 omega square. And here is a property omega cube is equal to 1. When we multiply these numbers, if we have a number omega cube, it is equal to 1, and omega 4 is equal to omega. All the entries in the set belongs to the set, therefore clear property hold. We have solved for associative property, it also satisfies. 1 is identity because multiplication, and inverse of 1 is 1, omega is omega square, because omega multiplied omega square is equal to 1, and omega square multiplied by omega also equal to 1. Then commodity property also hold, therefore this is an abelian group with respect to multiplication. And next question is like we have done in example, multiply both sides by A inverse and we get the answer. Here we have a number like a plus square root 3 and b, and a and b belongs to rational numbers, and square root 3 is the irrational. And we show that a set which contains all these numbers like this form a group. And we have two numbers x and y. If we add these two numbers, the resulting answer also in this form, therefore Clay property hold. In associative, we let three numbers x, y, z in this form, and we add these numbers at the end, we get the answer in same form, therefore associative property hold. For identity, 0 plus square root 3 is 0. Square root 3 is identity element. For inverse, minus a minus b square root 3 inverse for each of its element, and commodity property also hold, therefore this set is an abelian group. Next question is P of S with respect to intersection. Now we let set AB and then its power set. Then from power set we draw its table with respect to intersection. All the entries of the table belongs to the set, therefore clear property hold. We also solve associative property. Associative property also hold. Now we see that identity is S itself, because we intersection it with the sets, it shows the same answer, therefore identity is S, therefore this set is a monoid. Next we solve the table and show the missing values like that. And question number 10 is same. we have done in example matrices of 2 cross 2. Very important question. Same question repeat in example. And now here okay student, solve each question. This is an important exercise for board point of view. For long questions, if you have any problem, and I will solve it. Allah Hafiz.